Hi everyone, and welcome to my talk for VMSG 2022. My name is Pip Liggins. I am a final year PhD student at the University of Cambridge, and today I'm going to present some of the results from my work on modelling the volcanic atmospheres of rocky planets. As a brief introduction, when we talk about small Earth or super-Earth-sized exoplanets, they are often described as having atmospheres which are either primary or secondary in nature. Primary atmospheres are those that most planets form with, comprised of gases accreted directly from the protoplanetary disk, outgassed by the solid material which coalesces during the formation period, or later on gases released by any magma ocean stage. As small planets age, they will either lose their atmospheres completely, leaving just a bare rocky core, or they will see their atmospheres heavily modified into what are known as secondary atmospheres, of which one key modification process is volcanism. Planets which have these volcanically derived secondary atmospheres are particularly interesting because volcanism provides a long-term link between the atmosphere and the mantle beyond the magma ocean stage. This is key because in most cases, the only observations that astronomers will be able to make of exoplanets beyond their mass and radius will be of their atmospheres. This leads us to ask, what can we learn about the geology of a planet if all we can observe is its atmosphere? Specifically, can we learn anything about the key properties which might control planetary formation, such as the mantle FO2? Which is a measure of how oxidizing or reduced mantle is. This is a key parameter which links core formation processes and formation location in the disk. Knowing the rough mantle FO2 of a range of exoplanets would help constrain several theories around planet formation. Volcanic degassing, then, is the key link between the mantle which we wish to investigate and the atmosphere which we can observe. Critically, we know that the chemistry of volcanic gases will change according to the FO2 of the magma and hence the mantle from which it came. As the melt becomes more reduced, moving from right to left on this plot, the water and CO2 content drops, replaced by hydrogen and carbon monoxide. However, this plot only holds true if comparing the gases at the point which they are emitted from the vent. It is a set of gas compositions produced at a single pressure and at volcanic temperatures. So the question is, will these FO2 trends hold when observing a volcanically derived atmosphere if the surface temperature of the planet is not the same as that of the magma? The composition of volcanic gases is also pressure dependent, as controlled by the solubility laws. If you combine lots of volcanic gases together, or released from the same magma composition but at different pressures as the atmosphere grows, how will that affect the FO2 trend in gas speciation? So to model the volume and chemistry of volcanic gases as controlled by magma FO2, we used my thermodynamic degassing model, which I call EVO. This uses the equilibrium constant and mass balance method, where the mass of all the volatiles in the system, both in the melt and in the gas or fluid phase, is held constant, and a set of equilibrium constant equations for gas-gas reactions are solved simultaneously with a set of solubility laws. This means that at every pressure step, the gas is in equilibrium with the melt according to the solubility laws of water, CO2, sulfur, and methane and carbon monoxide at low FO2. The FO2 of the volatile system is also buffered by the iron in the melt, so at all points the gas phase is at the same FO2 as the silicate melt. The simultaneous equations are solved at every pressure step, from the point of volatile saturation all the way up to the point designated as surface pressure. As a quick side note, EVO is now publicly available on GitHub, as well as the planetary evolution cases it's been applied to that I'm discussing today. It's also currently in use on a set of projects covering a range of scales, from modelling Venus to studying the behaviour of sulfur in oxidized arc systems, so please do check it out for all of your degassing related needs. To model how volcanic gases accumulate in a planetary atmosphere over time, we embedded EVO into an evolution model. We initialize a mantle with a certain volatile content, and at every time step we apply batch mantle melting and put the resultant magma through EVO. As the atmospheric pressure gradually increases with the addition of volcanic gases through time, the pressure-sensitive solubility of these volatiles comes into play and the gas composition will change. Finally, the volcanic gas erupted is mixed into the pre-existing atmosphere. The whole thing is cooled or heated to the surface temperature. The recalculation of the atmospheric composition is done using FastChem, which is an ultra-fast gas equilibrium model. We chose to focus on planets with surface temperatures of around 800 Kelvin, which is slightly warmer than that of Venus, because below that temperature there's a risk that the atmospheric chemistry can't be approximated using thermochemical equilibrium, and therefore a full kinetics model would be required to calculate the composition of the atmosphere. As a quick reminder, this is what a typical high-temperature volcanic gas would look like according to the FO2 of the melt it degassed from. And once we allow for atmospheric cooling down to 800 Kelvin from around 1500, and the accumulation of volcanic gases in an atmosphere over time, these are the compositions we achieve, varying with mantle FO2. Hopefully you can see that the atmospheric composition has started to show distinct differences as the mantle FO2 has varied, compared to the more gradual change of the high temperature gas shown previously. To make these clearer, I'll first remove the species which don't change their abundance significantly with FO2, that is, the water, hydrogen sulfide, and nitrogen. Now these species are removed, the transitions become much more distinct. We found that the composition of these 800 Kelvin atmospheres after 1 gigayear of volcanic activity can be split into classes according to their chemical composition. Firstly, at the most oxidized end, from approximately wustite plus 2.5 and up, we have class O, indicating oxidized mantles. This is where sulfur dioxide is present along with other sulfur allotropes, and CO2 is the only carbon-bearing species present in significant quantities, although CO and COS are present at lower levels. There's also no ammonia in this class. As we get more reduced, down to just below the wustite buffer, we have class I, produced by intermediate mantle FO2. The oxidized sulfur species have disappeared, and there's a massive increase in the amount of methane which coexists alongside CO2, CO, and COS. Finally, class R, at the most reduced end, below the iron-wustite buffer, ammonia becomes more abundant than carbon monoxide, and COS is no longer present above ppm levels. So what we've ended up with is a set of 3 classes which could be used to identify the degree of oxidation in a planet's mantle for Venus-like surface temperatures, although not necessarily Venus-like pressures. These classes are established within 1 gig year of the onset of volcanism, and in the vast majority of cases where we varied the ratio of hydrogen to carbon in the initial mantle, they remained fixed over 10 gig year of evolution. We did find, however, that if the H2C ratio of volatiles is any less than Earth's, i.e. a planet is more carbon-rich or hydrogen-poor than Earth is, then class R atmospheres are not produced, regardless of how reduced a planet's mantle is. The model used to produce these results accounts for volcanic outgassing and the re-equilibration of the atmospheric chemistry according to the surface temperature. However, there are many other atmospheric processes we don't account for, which will inevitably change our results. Notably, we don't account for the fact that the atmospheric chemistry itself will control the surface temperature through climate. We also don't account for photochemistry in the atmosphere or atmospheric escape. I'll leave these summary points up for you to read. As of today, JWST is 3 days away from launch, so hopefully when this goes out, my final point is still relevant. Thank you for listening, and please do get in touch with any questions.